My name is Yujie Jiang. I am a third-year PhD student in statistics from Dr. Wenyi Wang's lab at MD Anderson Cancer Center. Glad to be here introducing our research progress on subclonal reconstruction. And the method I'm proposing today is called CliP. A little background here. Mutations in tumor cells accumulate over time, generating heterogeneous populations. The problem we want to solve is to infer the distinct populations in heterogeneous tumors based on the measured VAF of their somatic mutations. Essentially, we're doing a clustering of these mutations inside a tumor sample and investigate which clone or subclones do these mutations belong to. This is where our inspiration comes from. We're part of the PEACOCK study, an international collaboration to identify common patterns of mutations in over 2,600 cancer whole genomes from the International Cancer Genome Consortium. This graph shows many current methods for subclonal reconstruction used in PEACOCK. Most are based on the Dirichlet process, which is accurate but slow. Specifically, I would emphasize the WGS method, which is a well-known and widely used method published in 2015 that we'll use as to benchmark and compare with our method. All these methods are computationally intensive, creating processing time bottleneck in large-scale studies. Therefore, we developed a fast and accurate method called CliP, which is designed to reduce the processing time and distinguish the subclones quickly with minimal post-processing. Our model design is shown here. We assume our sequencing reads Ri follows a binomial distribution, while read depth follow a Poisson distribution. We also use the infinite site assumption, and we assume the CCF to be 1. The true proportion can be expressed as follows. We are interested in CCF or CP because SNVs from common subclones should have the same CCF and CP. A common binomial distribution is given as follows, but we cannot simply use it in our model. Instead, we propose this penalized likelihood function, where the penalty term could be SCAD, MCP, or any unbiased penalty. Penalty allows homogeneity and sparsity in cellular prevalence and helps us minimize bias aggregation. We choose SCAD because it returns the best result. To solve this optimization problem, we use ADMM because it provides huge computational advantages. Here is a plot of the speed of CliP comparing with WGS across different number of SNVs in different samples. They're both ran on the same machine with one core. The y-axis is the running time in seconds, with log 10 scale. We can see that CliP has a significant gain in computational speed in all cases. Our eventual goal is to help make discoveries in cancer evolution faster using CliP. As an example, we investigated the relationship between clonal fraction and immune proportion in colorectal cancer, combining data from PEACOCK and TCGA. In the plot, MSI and MSS stands for microsatellite instability and stability, respectively. CMS 1 to 4 stands for 4 different types of consensus molecular subtypes. Here, we observe a positive correlation between the two proportions within MSS patients, who are known to present limited response to immunotherapy. Within MSS CRC, younger tumors or patients with high clonal fractions are likely surrounded by a still effective immune environment. Correspondingly, these patients presented better survival outcomes, although this comparison was not statistically significant due to limited sample size. To sum up, CliP is the first to utilize a regularized maximum likelihood framework in subclonal reconstruction. Also, simulation studies show that it could be 100 times faster than MCMC-based algorithms without decreasing performance. Furthermore, it managed to work on regions either with or without CNAs. This is worth mentioning because many existing methods cannot work when there is no CNA. Here I'm showing that PEACOCK studies already include results from CliP. Furthermore, it could be applied to study evolutionary process and interactions between tumor development and immune responses in CRC. Here is a GitHub website for our software. Thanks for your attention.